Hello everyone. I welcome you all to my lecture on axial flow compressors. Last class we had a discussion on centrifugal compressors. Uh, Now, the working of axial flow compressors are slightly different. In this, the air flows through the compressor in a direction parallel to the axis of rotation, and the air is continuously compressed. Both the rotor and the stator blades will have a aerofoil shape. Now listen very carefully. I'll explain the construction of the axial flow compressors. It starts with the rotating drum. Now this drum is actually rotating. Please understand that it consists of two types of blades. One is fixed and the other one is moving. So the moving blades are called as rotor blades and the fixed blades are called as stator blades. Stator, stator and rotor. So the stator blades are marked with S and rotor blades are marked with R. Clear? Now it consists of adjacent rows of moving blades and fixed blades. So after a set of R blades there will be S blades. Understand that. A pair of R and S is called a stage. For example, this pair is called a stage. A pair of rotor blades and stator blade is called a stage. Clear? Now, I'll tell about rotor blades first. Now, these rotor blades are actually fixed on the drum. As you can see, the rotor blades will be fixed on the drum. So, as the drum rotates, the rotor blades also will rotate. And it will impart kinetic energy to the fluid. Clear? Now, the stator blades. Now, the stator blades are marked with S. Are marked with S. I'll mark it with red. Now these are the stator blades. They are actually fixed to the casing. They are fixed. They won't move. So it is fixed to the casing of the compressor. Now as you can see, when the fluid flows through the rotor blades, it imparts kinetic energy to the fluid. Now the fluid with high kinetic energy goes into the stator blades. In the stator blades what happens is it has diverging passages. Because of this the velocity decreases and its pressure energy increases. So it converts a part of kinetic energy of the fluid to pressure energy through the diffusion process carried out in the diverging blade passage. Now the stator blades also act as guide vanes. They direct the fluid to the next set of blades or the next stage of blades. That is why it is called as guide vanes. Now as you can see, the annular space. This is the annular space. I'll mark it with blue. This is the annular space, right? As you can see, the annular space goes on decreasing. And because of this, the velocity remains constant. And this aerodynamic, just look into the last line, the aerodynamic shape of the rotor and stator blades will help in reducing the shock, turbulence and boundary separation, thereby reducing the losses. So I hope you understood the construction very clearly. Next we will go into the working. So next is working. So in working, the compressors, the axial fluid flow compresses the fluid by first accelerating it and then diffusing it to obtain the pressure increase. So as I already told you, the work input to the rotor shaft is actually transferred to the air, which actually accelerates the fluid flow. The rotor blades will supply kinetic energy to the fluid, and these rotor blades are arranged in such a way that the path between these blades forms a diverging passage to the air, resulting in decrease in velocity and increase in pressure and enthalpy. Next, the air flows into the stator blades. Now in the stator blades also they have diverging passages which increases the pressure further. As I told you before, the stator blades also guides the fluid to the next stage. Now in the whole process, temperature rise remains same in the rotor blades as well as the stator blades, and the axial velocity remains constant. Clear? So next I'll explain the velocity diagrams for axial flow compressors. Now listen carefully. Now as you can see, these are the aerofoil rotor blades and these are the stator blades. Okay. Now there are two velocity triangles. This one is the inlet and here it is the outlet. This is the inlet part. Clear? And this is the outlet. Now in the inlet, the main difference from that of a centrifugal compressor is that all angles will be measured from the axial direction. Clear? Now this is the axial direction and all angles will be measured from this axial direction. Please understand that this is the axial direction, and all angles of the relative velocity, absolute velocity will be measured from this line. Clear? Now I'll tell all the terms, I'll explain all the terms. Now there is absolute velocity v1, then we have velocity u1, which is the vane velocity or the blade velocity. Then the relative velocity of v1 and u1, which is marked with vr1. Okay, now vr1 makes angle theta with the axial direction and v1 makes an angle alpha with the axial direction. Clear? Similarly, we have the outlet velocity triangle. V2 makes an angle beta with the axial direction. VR2 makes an angle phi with the axial direction. And VR2 is actually the relative velocity of V2 and U2. Clear? So just note these points for axial flow compressors. For an axial flow compressors, U1 will be equal to U2. That is, the blade velocity will be same because the air enters and leaves the rotor at almost equal radii. And the velocity of flow will be same for axial flow compressors. And due to the diffusion in the rotor blades, velocity decreases and pressure increases. That is, the velocity of air relative to the blade decreases, which simply means that VR2 will be less than that of VR1. World velocity will lie in the same plane. That is clearly evident from the figure. And since work is done on the air by the rotor, V2 will be greater than V1. Now theta phi is the angles made by the relative velocity VR1 and VR2 respectively at the inlet and outlet with the axial direction, and alpha beta are the angles made by the absolute velocity V1 and V2 with the axial direction. So please understand the terms very clearly. One notable difference from that of centrifugal compressor is that in centrifugal compressor we take all the angles from the horizontal direction, whereas in the case of axial flow compressors we take all the angles from the axial direction. Clear? This is V1, VR1, alpha, theta. I hope you have understood the velocity diagrams clearly. Next we will go into the work done of an axial flow compressors. That is the work done on the air by an axial flow compressor. Now, so first is work input to the air, that is work done on the air per second per stage. That is important. Per second per stage. It is given by W is equal to M into VW2 minus VWU1. You're familiar with this equation. We have used the same equation for centrifugal compressors also, where M is the mass flow rate, which is given by ρ1 Q1 equal to ρ2 Q2. The mass flow rate is constant. We can't say the same about discharge. You know the reason for that. Rho is density, Q is discharge. But U1 is equal to U2 is equal to U for axial flow compressors, which I have explained before. So I'll slightly modify the equation number 1 by taking u as the common factor. So our equation 2 becomes W is equal to M into VW2 minus VW1 into U. Clear? So the total work input per second, that is total work input per second, will be equation, this term, into number of stages. So this is the total work input per second. Now I'm going to write the equation 2 in terms of flow velocity. So from the inlet and outlet triangles we can write VW1 is equal to VF1 tan alpha, VW2 is equal to VF2 tan beta. So I'm going to substitute these two in equation 2. We'll get this as the equation. But for an axial flow compressors we know that VF1 is equal to VF2. So finally equation becomes W is equal to MUVF tan beta minus tan alpha. This is the equation number 3. So this is the work done on the air per second per stage. So in order to find the total work input, we'll multiply that with number of stages, which is this equation. Clear? Now we can find the thermodynamic equation also, which is given by MCP TO2 minus TO1, where TO2 and TO1 are total temperature or stagnation temperature, which I have previously explained. Clear? So next I'll explain what is degree of reaction. So degree of reaction is the ratio of static pressure rise in the impeller divided by total static pressure rise in the compressor. Clear? Now what we'll do is we'll find the expression for static pressure rise, total static pressure rise, and we'll modify the final equation slightly using the velocity diagrams. Now what is the equation for static pressure rise in the impeller? Now the static pressure rise in the impeller is actually given by the equation 1 by 2 m into VR1 square minus VR2 square. This is because when air passes through the set of rotor and stator blades through the diverging passages, the kinetic energy is reduced and which is converted into pressure energy. The static pressure rise is given by this equation. Now total pressure rise in the compressor is actually the work input by the compressor to the air, which is given by mu into VW2 minus VW1. So the degree of reaction becomes half m VR1 square minus VR2 square divided by mu VW2 minus VW1, which I'll take it as equation 1. We'll cancel out m as the common factor. Now from the inlet triangle, VR1 square, using Pythagoras theorem, VR1 square is equal to VF1 square plus U1 minus VW1 the whole square. Similarly, U minus VW1 is equal to VF1 tan theta. Clear? So we'll substitute that. You'll get as VR1 square is equal to VF1 square plus VF square tan square theta. I'll name it as equation 2. Similarly, from the outlet triangle, you will have equation number 3, which will give you VR2 square. From the inlet triangle itself, we can write tan alpha is equal to VW1 divided by V1, tan alpha. VW1 by VF1. So VW1 becomes VF1 tan alpha and VW2 becomes VF2 tan beta. So I'll substitute 2, 3, 4 and 5 in equation 1. So you'll get this equation, but VF1 is equal to VF2 for axial flow compressors. So the final equation becomes VF into tan square theta minus tan square phi divided by 2u tan beta minus tan phi. So if you closely look at the inlet and outlet triangle which I have drawn, in this page I have drawn only the inlet velocity triangle. So in the previous pages I have drawn both the triangles. Refer that, you can see the symmetry of inlet and outlet velocity triangles, which will give you that alpha is equal to 5 and beta is equal to theta. So I'll again modify this equation, uh, and you'll substitute phi for alpha and theta for beta, and this is a square minus b square form, right? So I'll expand that, tan theta minus tan phi into tan theta plus tan phi. So this gets cancelled out. So the degree of final equation for degree of reaction becomes Vf tan theta plus tan phi by 2u. So I hope you have understood what is degree of reaction and the derivation of it. If you have any doubts, please feel free to contact me. Thank you.